So friends, welcome once again to Civil Engineering Infrastructure. And now we have reached the most important, practical and result-oriented phase of this entire research journey. That is in part 2, where there will no longer be just theory. Now we will talk about actual engineering results, strength performance, durability analysis, and did the final engineering conclusion. And as you can see on this screen, today we are going to understand in detail aggregate particle packing optimization in wrap-based concrete. Meaning, the concept which we understood at the scientific level in part 1. Today we will see how successful the same concept actually proved to be in practical engineering reality. Because friends, engineering, just understanding the theory is not enough. Final decisions always take results. If a concept is not successful at the laboratory level, so no matter how good the theory is, its practical value remains limited. And this is the reason why this entire part is going to be very important. So far we have understood that RAP-IE reclaimed asphalt pavement material does not behave like conventional aggregate, because aged bitumen coating is present on its surface, which can create a bonding challenge between the cement paste and the aggregate, because of which weak bonding may develop, internal voids may increase, strength may reduce, and durability may also be affected. But then we also understood a possible engineering solution: particle packing optimization, where the idea was that if aggregates were scientifically optimized, and the particles should be arranged such that packing density should be improved, internal voids should be minimal, particle interaction should be better, so the performance of concrete can be significantly improved. But friends, now the biggest question is this: did this optimization actually prove successful? Has the strength of wrap concrete really improved? Did tensile performance improve? Has durability performance improved? And most important, did laboratory testing support this concept? Because as you can see on the screen, today we will not just talk about assumptions. We are going to see the actual laboratory testing results, where strength performance was evaluated through compressive testing machine. We will compare conventional concrete versus RAP-optimized concrete. And you will see that was there a measurable improvement after optimized particle packing? Or the improvement was limited only to the theoretical level? Along with this, we also analyzed durability performance too. Meaning, long-term behavior, how was it? Is material performance suitable for sustainable infrastructure or not? What real engineering limitations came to light? And finally, we'll also understand the final engineering conclusion of this entire research. Meaning, is not going to be just a normal lecture. This is the research validation phase, where theory will meet practical engineering reality. So watch the video till the end, because today we are going to find out wrap-based concrete can actually become the future infrastructure technology, or there are still many engineering challenges left in it. So friends, welcome once again to Civil Engineering Infrastructure. And now we have reached the most important, practical and result-oriented phase of this entire research journey. That is in part 2. Because till now we had understood the theory, science and methodology in detail. But now, it's time to look at actual engineering findings. And as you can see on this screen, this entire part 2, we are going to understand step by step that did optimized particle packing actually bring practical improvement in wrap-based concrete? Or the improvement was limited only to the theoretical level? Because friends, in engineering, facts are more important than assumptions. Actual results. And this is the reason why this entire part is going to be very interesting. Till now we have understood that due to aged bitumen coating on the surface of wrap aggregates, bonding issues may develop between the cement paste and the aggregate, because of which internal voids may increase, strength may decrease, weak edges may develop, and durability may also be affected. But we also understood that particle packing optimization, there may be a possible engineering solution to this problem, where aggregates are scientifically arranged in such a way that packing density should improve, internal voids should reduce, better particle interaction should develop, and the overall performance of the concrete can be improved. But the biggest question is, did laboratory testing support this theory? And friends, are going to understand step by step in this entire part 2. First of all, experimental results, where we will understand the actual test results. Meaning, what were the results of laboratory testing? What did the data analysis say? What did the performance observation reveal? Because final judgment in engineering research is not based on assumptions. Gives testing results. Next we will strength comparison, where we will compare conventional concrete versus wrap-based optimized concrete. And you will see that what was the actual difference seen in compressive strength? Did the wrap-optimized mix prove stronger? Or was the performance equal to or less than conventional concrete? After this we will understand in detail durability performance. Because just having good strength is not enough. Durability is equally important for real engineering applications. So we will see long-term performance, material behavior, structural reliability improved, and whether wrap-based concrete can prove to be durable in practical engineering conditions. It will increase after towards practical applications, where you will understand what is its scope in sustainable construction projects, how practical are the recycling benefits, where is real-world engineering use possible, meaning, can this technology become a part of the future construction industry? Or are there still many limitations in this? And then will come the most important phase. Limitations final conclusion, where we will understand what were the research challenges, what engineering limitations were encountered, how possible is the future scope, and what does the final engineering conclusion of the researchers say. I mean friends, is not going to be just a normal lecture. This is going to be an actual test of theory versus practical engineering reality. So watch the video till the end. Because today we are going to find out wrap-based concrete can become a strong engineering solution for future sustainable infrastructure. Or there are still many practical engineering challenges left in it. So let's go. Now let's start understanding the actual engineering results of this entire research step by step. Microstructure analysis, detailed voiceover. Now we have reached the deepest and most advanced part of this research. Microstructure analysis. WHAT is microstructure analysis. Now let us understand in a simple way. Microstructure analysis means to study the internal structure of the material at the microscopic level. THAT is things that we cannot see with our eyes. Analyze them with the help of a microscope is done. The case of concrete. WEC. Aggregate. Cement paste. The bonding zone between them. WHY microstructure is important? Now comes the question. WHEN we did the strength test. So why is there a need to look at the microstructure? BECAUSE strength only tells the result, but does not tell the reason. MICROSTRUCTURE tells us. Why did the failure occur? Why is bonding weak? What is the problem inside? I.E. Strength test what happened? Microstructure why happened? Interfacial transition zone it's. Now let's come to the most important concept. ITZ interfacial transition zone. What is this? THIS is the zone where aggregate and cement paste meet each other. THIS is the weakest zone of the entire concrete. Image explanation, right side. Image you see now is THIS is a microscopic image, clearly visible in wrap aggregate, cement matrix, and it's in the middle. THE its area looks different because its structure is different from other concrete. PROBLEM in wrap-based concrete. Now the most important thing. ITZ is even weaker in wrap concrete. Why? AGED bitumen coating is applied on wrap aggregates. This coating disturbs cement hydration, reduces bonding. WHAT is the result. It becomes porous. Microcracks develop, porosity and voids. Now let's understand a little deeper. Microstructure analysis reveals that where are the voids? How many are there? How are they distributed? If THERE are more voids, so density will decrease, strength will decrease. RAP concrete generally has higher porosity. ECT of particle packing. Now here comes the role of particle packing. If packing is optimized, there will be fewer voids. The particles will be tightly arranged. THIS improves the microstructure. I.E. Better packing, better its better strength. HYDRATION products overview. Now at the micro level we also see CEMENT hydration products as CSH gel, calcium hydroxide. If hydration is proper, will be dense, bonding will be strong. BUT in wrap concrete may be incomplete. Fewer products are made. The engineer's note says. Microstructure analysis gives deeper insight. Meaning, not just surface level. Rather, it tells the whole story inside. THIS analysis explains that S strength decrease or increase. PRACTICAL engineering insight. Now understand in real life. If you want to improve concrete, it's not just a mixed design. Rather, the microstructure also needs to be understood. BECAUSE real performance is decided from within. THAT, which cannot be seen with the eyes, is most important. FINAL takeaway. MICROSTRUCTURE internal reality of concrete. ITZ weakest and most critical zone. BONDING issues in wrap concrete are visible at the micro level. PARTICLE packing improves the microstructure. Results discussion. Now we have reached the most important and intelligent part of this research. RESULTS discussion. So far we have C. Experimental results. Data understood. But now the real question is, WHAT does it mean? HOW to interpret these results. What is results discussion? Results discussion means UNDRSTANDING experimental data and extracting engineering meaning from it. I.E. Results numbers. Discussion understanding. THIS part decides whether the research is valuable or not. Key observation 1. Particle packing improvement. First observation. IMPROVD particle packing reduces internal voids. Now let's understand this. WHEN the particles are well packed. So, voids between them decrease. ITS direct effect. Concrete becomes more dense. The structure is compact. Key observation 2. Voids versus bonding. Now the next important point. REDUCED voids lead to better bonding. WHY. Because when the voids are low, the cement paste surrounds the aggregate well. If ROM this increases contact area, bonding improves. I.E. Less voids better contact better bonding. Key observation 3. Bonding versus strength. Now the third point. ENHANCED bonding improves strength and durability. If the bonding is strong, is transferred properly, fewer cracks develop. ITS result. Increases compressive strength. Improves durability. BUT. The most important twist. Now here comes the most important engineering reality. THIS is all theoretically correct. But in actual wrap concrete, BONDING does not improve completely. Why? AGED bitumen coating. THIS coating does not allow direct attachment of cement paste. Makes it weak. SO. Packing improved. Reduced voids. But the bonding was not completely strong. Image explanation. Image now is SHOWING concrete cubes and the testing environment. IT represents observed results. Practical test outcome. SOME cubes are intact. Some are cracked. THIS shows that the performance is not uniform. The engineer's note says, PROPER interpretation is necessary. Meaning, JUST looking at the data isn't enough. YOU need to understand, where did the improvement take place? Where is the limitation? ONLY, then will the correct conclusion be drawn. DEEP engineering insight. Now let's understand this at a high level. ENGINERING. Not every improvement is a complete solution. PARTICLE packing. improves structure, but does not solve bonding issues. So, this is a partial solution, not a complete solution. Final takeaway. PARTICLE packing reduces voids. VOIDS reduction bonding improvement does. IMPROVS strength. But BONDING limitation remains in wrap concrete. SO improved, but the entire problem was not solved. Strength comparison. Now we have reached a very important and practical part. STRENGTH comparison. So far we have view individual results. Discussion understood. Now we will DIRECT comparison between different concrete mixes. WHY strength comparison. Now the question. WHY is comparison so important? BECAUSE. Single value doesn't tell anything. Improvement is understood only when compared. I.E. Without comparison no conclusion. WHAT is compared. Here's how the researchers compared. CONVENTIONAL concrete. RAPBASED concrete with optimized particle packing. THIS comparison shows that. How efficient is wrap concrete? Is it suitable for practical use? Key observation 1. Optimized packing. First point. OPTIMIZED packing increases concrete density. WHEN particle packing is correct. Aggregates are tightly arranged. Voids are reduced. THIS makes the concrete dense. Key observation 2. Density versus strength. Now the important relation. HIGHER density higher strength. WHY. Because less voids better load transfer. Internal structure becomes stronger. I.E. Dense concrete strong concrete. KY observation 3. Wrap performance. Now the most important finding. RAP mixtures show comparable performance. WHAT does it mean? Wrap concrete is not completely weak. With the right mix design, it can be usable. I.E. Proper design comparable strength. GRAPH explanation, right side. Now let us understand the graph carefully. AEFT side, conventional concrete. RIGHT side, wrap-based concrete. THE graph shows APPROXIMATLY plus 15% improvement in wrap concrete. WHAT does it mean? Particle packing optimization is effective. There has been a measurable improvement in strength. But IT is important to pay attention. THIS improvement does not happen in every case. It depends on mix design, wrap quality, processing. The engineer's note says, STRENGTH comparison decide practical feasibility does. I.E. LUB result real application. DECIDD by comparison. Can it be used in the material field? Is it safe and reliable? REAL engineering insight. Now let's understand this in a practical way. IF the strength of wrap concrete. Very rarely reject. Equal acceptable. Improves highly valuable. THE case here. CONPARABLE bata slightly improved. WHAT does it mean? Wrap concrete future sustainable material. But LIMITATIONS still exist. Bonding issue. Its weakness. SO. Smart mix design is essential. If you understand completely till here and you find this level valuable, so subscribe to the channel now and press the HE bell icon. You do not miss such deep civil engineering concepts. Final takeaway. STRENGTH comparison decision making tool. OPTIMIZDD packing density improvement. DNSITY strength improvement. RAP concrete comparable performance achieved. Concrete laboratory strength testing. So far we have understood what are wrap materials, particle packing works, what are optimization techniques, and what do the experimental results say. Now we are entering the most practical phase of this entire research. CONCRETE laboratory strength testing. WHY laboratory testing. Now comes the question. Are just theory and models enough? The answer is no. Because real performance is always proven through lab testing. Theoretical improvement is not valid until confirmed by testing. I.E. What you design, what you get. Validation is required. WHAT happens in this phase. This phase we will look at. HOW concrete samples are tested. IS their strength measured. HOW wrap-based concrete compares to real conditions. THIS entire section will focus on compressive strength, density behavior, bonding performance, visual understanding. You can see on the screen CRUSHED concrete cubes. IT shows failure pattern, internal structure response, behavior under load. ITS not just an image. THIS is the whole story of concrete performance. WHAT you should focus on. Now you have to pay attention to the next slides. HOW the load is applied. HOW does failure occur. HOW is strength calculated. BECAUSE this is what decides whether the concrete is usable or not. Will the structure be safe or not? REAL engineering perspective. Before using any material on the site, IT is tested in the lab. IF lab fails, material reject. IF lab pass, only then use in field. SO. Lab testing final approval stage. ACCTIO in transition. Now in the next slides we will see step by step. TSTING procedures. HOW the machine works. THE results come. AND most important. HOW strong is wrap concrete. Sustainable highway construction. Have reached the last and most important part of this entire discussion. SUSTAINABLE highway construction. Big picture. So far we have seen what are wrap materials, particle packing works, how strength and durability are improved, where are the practical applications. NOW all of this adds up to a big question. WHAT should the future infrastructure be like? Need for sustainability. The construction industry today is facing resource shortage, environmental pollution, high carbon emissions, traditional construction methods consume more natural resources, have a negative impact on the environment. SO. WE need sustainable solutions. ROLE of recycled materials. This is where materials like RAP become very important. WHY. Waste material is reused. Landfill is reduced. Natural aggregates save. I.E. Waste resource transformation. Application in highways. Highway construction is an area where too much material is used. Large-scale projects occur. RAP is used here. Cost is reduced. Improves sustainability. Reduces environmental impact. A&D. This is the future. ECOFRINDLY highways. Visual understanding. You can see on the screen. REAL highway construction scene. ITS not just construction. IT shows modern engineering. Sustainable approach. Large-scale implementation. Engineering vision. Important mindset for future engineers. JUST building strong structures. RATHER. Sustainable. Economic. Environment friendly. Designing solutions. Final insight. RAPBASED concrete is a powerful solution. OPTIMIZED correctly. It can replace traditional materials. Can provide long-term performance. Can achieve sustainability goals. Final conclusion. If this entire study. Optimized particle packing. Improved strength durability. Reduced environmental impact. A&D. This combines to make SUSTAINABLE infrastructure. Sustainability benefits of RAP. Now we understand sustainability at a deeper level. Not just a concept. RATHER. What are the actual benefits? WHAT is sustainability in construction. Sustainability means using resources in such a way that they remain available for future generations. I.E. Less waste. Less pollution. More efficiency. Problem with traditional construction. In traditional construction methods, a lot of natural aggregates are used. Demolition waste increases. Pressure on the environment increases. RESULT. UNSUSTAINABLE development. ROLE of RAP game changer. This is where RAP becomes a very powerful solution. BECAUSE RAP is already used material. Comes from waste. Can be reused. I.E. Old roads new infrastructure. ACT. Reduction in construction waste. First benefit. WASTE reduction. WHEN asphalt roads are recycled. Reduces waste going to landfill. Disposal problems are reduced. If ROM this. REMAIN is clean. Though. Conservation of natural resources. Second major benefit. NATURAL aggregates survive. IF using RAP. Reduces quarrying. Natural materials are conserved. I.E. RESOURCES are saved for the future. 3. Reduction in environmental impact. Now the biggest impact. ENVIRONMENT protection. BY using RAP. Energy consumption is reduced. CO emissions are reduced. Reduces overall carbon footprint. IT directly contributes to IN green construction. Visual understanding. You can see on the screen. RECYCLING process. IT shows Old material is being collected. Processing is underway. And then getting reused. THIS is the concept of circular economy. Engineering perspective. Important thing for today's engineers is sustainability cannot be ignored. EVRY project requires consideration. How much is the cost? How is the performance? What is the impact on the environment? RAP balances all three. Final takeaway. RAP is not just a material. THIS is one approach. Waste reduction, resource conservation, environmental protection. And this is the future. Sustainable infrastructure development, environmental impact reduction. Now we understand sustainability in a more specific way. Environmental impact reduction. WHAT is environmental impact. Environmental impact means how much impact do construction activities have on the environment? This includes waste generation, resource depletion, air pollution, carbon emissions. THIS impact is much greater in traditional construction. RAP helps. Reclaimed asphalt pavement significantly reduces this impact. HOW. By reusing waste. By saving natural resources. By reducing energy consumption. I.E. Less damage to environment, more efficient construction. ACT. Reduction in landfill waste. First impact. LNDFILL waste reduction. WHEN asphalt is recycled. Old material is not dumped. Reduces the load on landfill sites. FROM this. Land pollution is reduced. Waste management is easier. Though. Reduced extraction of natural aggregates. Second important factor. AES is mining butta extraction. BY using RAP. Reduces quarrying. Natural ecosystems are protected. BECAUSE. REMOVING aggregates is harmful to the environment. 3. Lower carbon emissions. Now the most critical factor. CARBON emissions. TRADITIONAL construction. High energy consumption. More CO release. BUT using RAP. Energy requirement is low. Transportation may also be reduced. Emissions are reduced. IT directly contributes to IN climate change mitigation. Visual understanding. You can see on the screen. RECYCLING plant butta construction site. IT shows material reuse, processing, environmental friendly operation. ITS not just construction. THIS is responsible engineering. ENGINERING responsibility. For today's engineers, environmental responsibility is not optional. EVRY project requires consideration. Impact on the environment. Long-term sustainability. Resource efficiency. RAP practically implements this idea. Final takeaway. The use of RAP is not just for cost or performance. RATHER. REDUCE fill land waste. Save natural resources. Reducing carbon emissions. And this is what makes it environmental responsible infrastructure. But these limitations of RAP-based concrete. So far we have seen the advantages and performance benefits of wrap. Like any engineering material, wrap also has some limitations. And it is very important to understand these so that we can make the right design decisions. 1. Bitumen coating issue. The first limitation is bitumen coating. The surface of wrap aggregates. There is an aged bitumen layer. THIS creates the problem. Proper bonding is not possible with cement paste. RESULT. WEAKER interfacial transition zone. It's A&D from this. Strength may decrease. Durability may also be affected. Though. Effect of excess wrap content. Second limitation. HIGH wrap percentage. If wrap is used too much, overall strength may decrease. WHY. Weaker bonding. Different material behavior. SO. If wrap should be optimized. ONE should not blindly use maximum. 3. Need for proper mix design. Third and most important thing. PROPER mix design is critical. In wrap concrete. Material variability is high. Properties are not consistent. SO. Careful proportioning. Testing. Optimization. ALL this becomes necessary. Engineering perspective. THIS does not mean that wrap is a bad material. RATHER. IS a sensitive material. WHICH depends on mix design, percentage used, processing quality, final takeaway. RAPBASED concrete is useful. BUT. Correct understanding is important. Limitations should not be ignored. BECAUSE. Although wrap has many benefits, it also comes with certain limitations. Future scope of wrap technology. Till now we have understood almost all the important things about wrap-based concrete, like what are its materials, what are its properties, how is the testing done, what are the results, and also seen some of its limitations. Now in this slide we will talk about its future, that is, how far wrap technology can go in the coming time and how much its role can increase in the construction industry. The construction industry today, we can see a significant shift. Previously, the focus was primarily on strength and cost, but now the focus is gradually shifting towards sustainability. This means that now engineers do not just want to build strong structures, but also want to build such structures which cause less damage to the environment, save resources, and are sustainable in the long term. And in this context, wrap emerges as a very important material because it is a recycled material which converts waste into a useful product. Now if we specifically talk about the points of this slide, then the first point is that advanced recycling technologies will be developed in the future. The recycling processes currently in use are basic, such as crushing and screening, but they will see significant improvements in the future. Machines will be more advanced, processing will be more controlled, and removing unwanted impurities will be easier. This will directly improve the quality of wrap aggregates. When the material quality is good, the concrete's performance will automatically improve. From an engineering perspective, the more uniform and clean the input material, the more reliable the output. Therefore, recycling technology will directly enhance the performance of wrap in the future. Now comes the second point of improved mix design techniques. The biggest challenge for wrap concrete right now is its behavior. It is slightly unpredictable because it has a bitumen coating on it and its properties are different from natural aggregates. But in the future, mixed design methods will become more advanced. Engineers will be able to better understand how much wrap to use, in what proportions, and how to optimize particle packing. This will reduce trial and error and result in a more accurate mixed design. When the mixed design is correct, voids will be reduced, density will increase, bonding will improve, and ultimately both strength and durability will improve. This means that in the future, the performance gap of wrap concrete, which is currently slightly less than conventional concrete, can be reduced to a great extent. Now the third point is wider adoption of sustainable road construction practices. This simply means that in the future, the use of wrap will not be restricted to limited projects, but it will be used on a large scale, such as in highways, expressways, and major infrastructure projects. The reason for this is also clear: wrap is cost-effective, easily available, and most importantly, it is environment-friendly. Nowadays, governments are also promoting sustainable construction, and in many places policies are also being made in which the use of recycled materials is encouraged. Therefore, in the future it is possible that wrap will no longer be an optional material but will become standard practice, especially in road construction. If we look at it overall, the main message of this slide is that wrap technology is still in the developing stage, but its potential is very high. Today there are definitely some limitations, but as technology improves, research progresses and mixed design techniques become better, these limitations will reduce. So as an engineer, it is important for us to understand that wrap is not just a recycled material, but it can become an important part of future construction, which will help us in providing sustainable, economical and efficient solutions. Industrial implementation of wrap. Till now we have understood the future scope of wrap, that its importance is going to increase further in the coming times. Comes a very practical question. Is wrap limited to theory and research, or is it actually being used in real-world projects? So in this slide we understand how wrap is being implemented at the industrial level. If we look at the global level, wrap technology is already being used successfully in many infrastructure projects. This is not just an experimental material, but has been adopted in real construction projects, especially in the road construction sector. The main reason for this is its two major advantages: economic benefit, cost saving; environmental benefit, waste reduction. When construction companies use wrap, they have to purchase fewer new aggregates, which reduces overall project costs. Plus, reusing old asphalt material also reduces landfill waste, which is great for the environment. Now, if we specifically talk about its applications, then the first use is in highway rehabilitation projects. HIGHWAY rehabilitation means repairing or upgrading existing roads. When a road becomes old or its surface gets damaged, instead of completely removing it and replacing it with new material, the same old material can be recycled and reused. This is where the use of wrap is very effective. In this process, the old asphalt pavement is removed, processed, and then used in the new pavement. This has two advantages. There is no material waste. Cost is significantly reduced. Now the second application is in the base and binder layers. Pavement structure is generally made up of multiple layers: base layer, bottom support layer, binder layer, intermediate layer. Wearing surface top layer. Wrap is specially used in the base and binder layers because structural support is more important there and the surface finish is not as critical as in the top layer. If wrap is used with proper mix design, it can provide sufficient strength and stability in the layers. Now the third point is adoption in sustainable infrastructure programs. Nowadays many countries are following sustainable development goals, which focus on resource conservation and environmental protection. RAP plays a very important role in these programs because it directly implements the recycling concept. Governments and organizations now also look at the amount of recycled material used in projects while approving them. Therefore, the use of RAP is increasing not only for technical reasons but also at the policy level. Now if we understand the engineer's note, then a very important thing has been said in it. SUCCESSFUL industrial implementation of RAP is possible only when proper quality control and optimized mix design are followed. This means that just using RAP is not enough. If the material is not processed properly or the mix design is not correct, performance issues may occur. Therefore, engineers have to keep in mind that the quality of RAP should be checked. Correct proportion should be maintained and should be used only after proper testing. If all this is done correctly, RAP can prove to be a reliable and efficient material at the industrial level. So overall, if we understand this slide, it becomes clear that RAP is not a future concept, rather it is already being used in real-world applications. And with the right techniques, its use can increase even further. Performance evaluation of RAP concrete. So far we have understood the industrial implementation of RAP, which makes it clear that RAP is not just a theoretical concept, but is being actively used in real-world projects. But now comes the most important question. Is RAP-based concrete really reliable? Can it deliver long-term performance? The answer to this question is found in this slide, where we understand the performance evaluation of RAP concrete in detail. Performance evaluation means strength, durability, and overall structural behavior of concrete to analyze to do. If RAP concrete is to be used in large-scale construction, this step is most critical. Now let us understand the points of the slide in detail. The first point is mechanical strength analysis of RAP concrete. It checks how much load the concrete can bear. For this, compressive strength test is performed, in which load is gradually applied on the specimen until it fails. If the proportion of RAP is optimized, its strength can be equal to conventional concrete. But excess RAP can reduce strength, so balance is crucial. Now the second point. Evaluation of bonding between aggregates and cement matrix. This is the most sensitive part of RAP concrete. RAP aggregates have a bitumen coating, which can weaken the bonding with the cement paste. If the bonding is weak, cracks will develop and the structure may weaken. Therefore, its interfacial transition zone and microstructure analysis is done. Due to strong bonding, load transfer is efficient and durability also improves. Now the third point. Assessment of durability and long-term performance. This checks how the concrete will handle environmental conditions over a long period of time. In this, factors like permeability, weather resistance, and chemical resistance are evaluated. If voids are less and packing is good, water penetration will be less and durability will increase. This significantly improves the service life of the structure. Now let us understand engineer's note. IT said that comprehensive performance evaluation is necessary to ensure the reliability of wrap concrete. This means that we have to check not only the strength but also the bonding and durability equally. We confidently use wrap concrete in real construction projects. It's clear from this slide that proper testing and evaluation of wrap concrete is very important before using it. If properly evaluated and optimized, wrap can become a strong, durable, and sustainable alternative. And if you want to understand such detailed concepts of civil engineering in simple language, please subscribe to the channel. Like the video. Share it with your friends. Useful knowledge can reach more people. Final conclusion. Now we have reached the last part of this entire presentation, where we understand the main conclusion of our entire study. It is clear from this research that SIGNIFICNTLY improves the performance of wrap-based concrete. When aggregates are arranged correctly, the spaces between them, i.e. internal voids, are reduced, making the concrete more dense and strong. Now let us understand the main points of the slide in detail. IMPROVD packing reduces internal voids. Particles of different sizes fill the gaps between each other, the empty space inside the concrete reduces. This reduces weak zones and makes the overall structure more compact. BETTER bonding enhances compressive strength. When voids are less, the bonding between aggregates and cement paste becomes better. This distributes the load evenly and increases the compressive strength of the concrete. RAP materials can be effectively used for sustainable construction. Wrap materials are reused, which reduces the demand for natural aggregates and also reduces construction waste. This makes it a sustainable and cost-effective solution. Now let us understand engineer's note. A promising solution for sustainable infrastructure development. This means that wrap could become a material playing an important role in future construction. Final understanding. If we summarize the entire study, then RAP concrete with correct mix design and optimized particle packing. It can become a strong, durable, and sustainable alternative. PROFESSIONAL closing. So in conclusion we can say that wrap-based concrete not only maintains structural performance, rather it also reduces the environmental impact. Therefore, using wrap in future infrastructure development can prove to be a smart and responsible approach. Future research directions. So far we have understood the performance, applications, and conclusion of wrap-based concrete. After every research, an important question arises. WHAT next? HOW, can this technology be made better? The answer to this question is given in this slide, where we will understand the future research directions. In which areas improvement and research is needed so that wrap technology can be made more effective. It is mentioned at the beginning of the slide that FURTHER research can expand the applications of wrap materials through improved mix designs and advanced testing techniques. Is still a lot of scope for improvement, especially in mix design and testing methods. Now let us understand the main points of the slide in detail. DEVELOPMENT of high-performance wrap concrete mixtures. This is the most important area of future research. Currently, the performance of wrap concrete depends largely on the mix design. If we develop mix designs that balance strength, durability and workability, so wrap concrete can perform even better than conventional concrete. New admixtures, better gradation control, and optimized particle packing techniques can be used in this. INVSTIGATION of long-term durability behavior is another very critical aspect. So far, most studies focus on short-term performance, but real-life structures have to last for years. Therefore, in future research it is important to see that how wrap concrete behaves over time. Effect does weather, moisture, and chemical exposure have on it? This allows for a better understanding of long-term reliability. INTGRATION of advanced optimization techniques. This is a modern approach to improve wrap technology. Computational models, artificial intelligence, and optimization algorithms can be used in this, so that the best possible mix design can be automatically identified. This will reduce the trial and error approach and increase accuracy. WHAT next. HOW, can this technology be made better? The answer to this question is given in this slide, where we will understand the future research directions, in which areas improvement and research is needed so that wrap technology can be made more effective. It is mentioned at the beginning of the slide that FURTHER research can expand the applications of wrap materials through improved mix designs and advanced testing techniques. Is still a lot of scope for improvement, especially in mix design and testing methods. Now let us understand the main points of the slide in detail. DEVELOPMENT of high-performance wrap concrete mixtures. This is the most important area of future research. Currently, the performance of wrap concrete depends largely on the mix design. If we develop mix designs that balance strength, durability and workability, so wrap concrete can perform even better than conventional concrete. New admixtures, better gradation control, and optimized particle packing techniques can be used in this. INVSTIGATION of long-term durability behavior is another very critical aspect. So far, most studies focus on short-term performance, but real-life structures have to last for years. Therefore, in future research it is important to see that how wrap concrete behaves over time. Effect does weather, moisture, and chemical exposure have on it? This allows for a better understanding of long-term reliability. INTGRATION of advanced optimization techniques. This is a modern approach to improve wrap technology. Computational models, artificial intelligence, and optimization algorithms can be used in this, so that the best possible mix design can be automatically identified. This will reduce the trial and error approach and increase accuracy. Now let us understand engineer's note. It has been said that future research will further enhance the practical implementation of wrap technology, meaning the limitations that exist now can be overcome through research, and wrap can be used more confidently in large-scale infrastructure projects. OVERALL understanding. The main message of this slide is that RAP technology is still evolving, and in the times to come, through research and innovation, it will become more efficient, reliable, and widely acceptable. So if we continue research in the right direction, so wrap can become a major sustainable solution for the future construction industry. Summary of research findings. Till now we have understood the entire research in detail. Be it mix design, testing, performance evaluation or conclusion. In this slide we will summarize the key findings of the entire study. This means that we will now put together the main results that have emerged from this research. It is mentioned at the beginning of the slide that OPTIMIZEDD particle packing effectively improves the performance of wrap-based concrete. Meaning this technique is the core concept of the entire research, which has improved the overall quality of concrete. Now let us understand the main points of the slide in detail. IMPROVD packing density reduces internal voids. When particle packing is optimized correctly, so the empty spaces between the aggregates, i.e. internal voids, are reduced. Fewer voids mean the concrete becomes more dense and compact. Both its strength and durability improve. ENHANCED bonding between wrap aggregates and cement. When voids are less, the bonding between aggregates and cement paste becomes better. This bonding is very important for wrap concrete, because wrap aggregates have a bitumen coating on them which can affect the bonding. But due to optimized packing, the bonding improves and load transfer happens efficiently. INCREACD compressive strength and durability. When the density increases and bonding improves, so it has a direct effect on compressive strength and durability. Concrete can bear heavy loads and resist environmental conditions for a long time. This makes wrap-based concrete more reliable for practical applications. Now let us understand engineer's note. IT states that optimized particle packing significantly enhances the structural efficiency of wrap-based concrete. This means overall performance, strength, durability and stability all improve. OVERALL understanding. If we summarize the entire research, then OPTIMIZEDD particle packing is the key technique for performance improvement of wrap concrete. And this technique establishes it as a strong and sustainable alternative to conventional concrete. After this slide we will move towards final closing, where we will professionally conclude the entire presentation. Engineering significance. Till now we have understood the technical aspects, testing, results and future scope of wrap-based concrete. Now in this slide we will understand that the actual significance of this entire research in the engineering field. THI is important for engineers in the practical world. It is mentioned at the beginning of the slide that if this research provide valuable insights into improving the design and application of recycled materials. Meaning this research is not limited to theory only. Rather, it helps engineers make better decisions in real construction projects. Now let us understand the main points of the slide in detail. PROMOTE is Sustainable Infrastructure Development. The biggest impact of this research is on sustainability. Using wrap materials reduces the demand for natural resources and also reduces construction waste. This makes eco-friendly infrastructure development possible. Is very important in today's time. IMPROV's efficiency of recycled construction materials. Previously, recycled materials were considered less efficient. But this research showed that their efficiency could be significantly improved through optimized particle packing. That recycled materials can now be confidently used in high-performance applications. SUPPORT is environmentally responsible engineering practices. This point is related to engineering ethics and responsibility. In today's time, the responsibility of engineers is not just to build strong structures. Rather, protecting the environment is equally important. RAP technology helps achieve this balance. Performance is also maintained, and the environmental impact is also reduced. Now let us understand engineers' note. IT said that engineering innovations play a key role in advancing sustainable construction technologies. That through new technologies and research innovations, we can make the construction industry more efficient and eco-friendly. Overall understanding. If we summarize this slide, then THI's research provides engineers with a practical solution, which is strong, economical, and also environmentally sustainable. It's not just a material improvement. Rather, it is an approach that defines the future direction of the construction industry. Now after this we will move towards final closing, where we will professionally conclude the entire presentation and connect with the audience. Practical benefits. So far we have understood the technical aspects, performance evaluation, and engineering significance of RAP-based concrete. In this slide we will focus on the most important thing: IT's practical use. WHAT are its actual benefits in real-world construction projects. It is mentioned at the beginning of the slide that OF RAP materials provides many practical benefits in modern infrastructure projects, meaning it is not limited to research only. Rather, it can be used directly in field applications and provides measurable benefits. Now let us understand its main points in detail. REDUCED construction material costs. Cost is a big factor in the construction industry. When we use RAP materials, we have to buy less new aggregates and raw materials. This significantly reduces the overall project cost. In large-scale projects such as highways, expressways, and urban infrastructure, this cost saving is very impactful. Efficient utilization of recycled resources. This point is related to resource management. RAP materials are basically recycled asphalt, which would otherwise have become waste. But when we reuse them, then reduces waste. There is efficient utilization of resources. Supports the circular economy. This means we are using existing materials to their maximum value. IMPROVD sustainability of infrastructure development. This is the most important long-term benefit. Sustainability is the biggest requirement of the construction industry today. By using RAP materials, reduces environmental impact. Carbon footprint is reduced. Natural resources are conserved. This makes infrastructure development future-friendly. Now let us understand engineers' note. IT said that practical implementation of RAP technology supports cost-effective and environmentally friendly construction. Meaning, THI's technology is not just in theory. Rather, it can be successfully applied in real projects. And IT simultaneously saves cost and protects the environment. Overall understanding. If we summarize this slide, then RAP technology provides a solution for the construction industry, which is economical, efficient, and sustainable too. It is a practical and reliable approach for future infrastructure development. Technological advancements in RAP recycling. Till now we have understood the performance, benefits, applications, and practical implementation of RAP materials. Now in this slide we will focus on a very important aspect, role of technology. It is mentioned at the beginning of the slide that MODERN technology has significantly improved the efficiency and performance of RAP recycling. This means that the recycling processes that were previously limited and less efficient. Today, due to advanced technology, they have become more accurate, faster and reliable. Now let us understand the three main points of the slide in detail. ADVANCED asphalt recycling plants. Nowadays, highly advanced plants are being used for asphalt recycling. These plants have controlled temperature systems, have better mixing mechanisms, precise material proportioning occurs. This makes processing RAP materials more efficient and consistent. Earlier, material quality used to vary in traditional methods. But now modern plants ensure uniform quality. AUTOMATED material processing systems. Automation has taken RAP recycling to a new level. Now manual dependency has reduced and sensors, digital control systems, automated feeders is used. From this, human error is reduced, increases process accuracy, production speed improves, meaning the overall system becomes more reliable and efficient. IMPROVD pavement recycling techniques. This point is directly related to field application. Today new recycling techniques have been developed such as hot in-place recycling, cold recycling, full-depth reclamation. With the help of these techniques, existing pavement can be reused efficiently. Reduced construction time. Cost also reduces. And most important, the environmental impact is also significantly reduced. Now let us understand engineer's note. IT is said that technology plays a key role in increasing the efficiency of recycled construction. Meaning, if the technology is advanced, then the recycling process will also be efficient. And the quality of the final construction material will also be better. Overall understanding. If we summarize this slide, then MODERN technological advancements are a major reason for the success of RAP technology. Technology has made the process faster, improved the quality, and enhanced sustainability. Implementation challenges. So far we have understood the advantages, applications, global usage and research contributions of RAP technology. Like any engineering solution, challenges is associated with it as well, are very important to understand and address. It is mentioned at the beginning of the slide that RAP technology offers many advantages, but some challenges have to be handled during implementation. Meaning, technology is good, but without proper planning and control, desired results will not be achieved. Now let us understand all three challenges in detail. Variability in recycled materials. This is the biggest challenge of RAP technology. Recycled materials are not always uniform. Come from different sources. What does it mean? Aggregate size variation is possible. Bitumen content may vary. Material properties may be inconsistent. Due to this variability, designing a mix becomes a little complex. So engineers, PROPER testing and characterization has to be done. so that consistent performance can be ensured. PROPER quality control during mixing is another very important challenge. If the mixing process is not controlled properly, so the quality of the final concrete is directly affected. Here engineers have to be careful. Correct proportioning, uniform mixing, temperature control. If any of these things go wrong, so both strength and durability can be compromised. Therefore, quality control becomes a critical factor. FILD performance monitoring. This challenge is related to long-term performance. The results in the lab can be good, but real field conditions are different. Traffic load, environmental exposure, moisture variations. Therefore, field monitoring of wrap-based pavements is necessary. This helps engineers understand that HOW the material is performing under actual conditions. And if there is any issue, it can be addressed timely. Now let us understand engineer's note. IT is said that it is important to address the engineering challenges carefully, only then the project will be successful. Meaning, HAVING challenges is not a problem. Ignoring them is the problem. If we handle these challenges properly, so wrap technology can become very effective and reliable. OVERALL understanding. If we summarize this slide, then RAP technology is powerful, but it needs to be implemented correctly. It requires proper material selection, requires strict quality control, and requires continuous monitoring. When all these things are done correctly, get its full benefit. Future innovations in wrap technology. Till now we have understood the past and present aspects of wrap technology, its benefits, applications, challenges, more research contributions. Now we come to the most interesting part in this slide. FUTURE. It is mentioned at the beginning of the slide that FUTURE developments in materials science and engineering will further enhance wrap technology. Meaning, RAP technology is still evolving, and in the coming times it will become even more advanced and efficient. Understand its three main future innovations in detail. SMART infrastructure materials. In the future, construction materials will not only be passive, will become smart. Smart materials mean can monitor their own condition, can detect damage, and sometimes may even show self-healing properties. When such smart materials are integrated with wrap technology, so ROADs and pavements will become more durable and intelligent. This will reduce the maintenance cost and increase the lifespan. ADVANCED recycling techniques. Recycling techniques are still continuously improving. In the future, more efficient processing methods will emerge. Energy consumption will be reduced, and material recovery will be better. What does it mean? RAP materials can be reused with higher quality, and this can result in performance equal to or better than traditional materials. DIGITL monitoring of pavement performance. This is the most modern and impactful innovation. In the future, roads and pavements will be digitally monitored. Sensors, IoT devices, data analytics. Through this will allow engineers to get real-time data on WHAT condition is the pavement in, WHERE the damage begins. WHEN is maintenance needed. This will make proactive maintenance possible, and sudden failures can be avoided. Now let us understand engineer's note. Thank you. Final closing. In this entire session we discussed wrap-based concrete technology and understood particle packing optimization in detail, where we learned how to use recycled materials properly. Not only does it improve performance, rather it also strengthens sustainable infrastructure development. This is not just a topic. Rather, it is an important direction of future civil engineering. WHAT you can do next. CONTINUE learning civil engineering concepts. EXPLORE sustainable construction technologies. UNDERSTAND real world infrastructure applications. And most important, STAY connected with civil engineering infrastructure. Keep getting such practical and field-based knowledge. If you found this content valuable, so support civil engineering infrastructure. Subscribe on YouTube. Press the bell icon so that you don't miss any updates. Share it with your friends who are in civil engineering field. This is not just a channel. It is a learning community where we all grow by sharing knowledge. ENGINERS note. Knowledge sharing is that foundation which makes the engineering community stronger and improves future infrastructure. Thank you so much to be a part of this entire learning journey. We will meet again soon with a new topic and practical insights.